All right. Well, we've started using the central limit theorem for means in 7.1, and we use the central limit theorem for sums in 7.2, and we're actually just going to kind of recap those again for this in 7.3 about means and sums. All right, so it's important for you to understand when to use the central limit theorem. If you're being asked to find the probability of a mean, then use the central limit theorem for the mean. If you're being asked to find the probability of a sum or a total, then you can use the central limit theorem for sums. They really work a lot the same way. And this also applies for percentiles for means and sums. If you're being asked to find the probability of an individual value, you are not using the central limit theorem. It's only about means, like a bunch of values. There's always an n, right? A number in the sample size for the number that you're averaging or the number that you're adding up. You have to have that for the central limit theorem. This is not for this individual random variable. So let's look at an example of what I'm talking about. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution, remember that guy? With the lowest stress score being equal to 1 and the highest being equal to 5. We are going to use a sample of 75 students. All right. First, let's find the probability that an individual student's stress score is less than 2.85. So we want to find the probability that x is less than 2.85 for the random variable x. Remember, it told us that the individual stress scores followed a uniform distribution where the lowest value is 1 and the highest value is 5. So x is distributive uniform 1, 5. Now, when we computed these percent probabilities, when we did this section, and it was like 6.2 maybe 6.1, 6.1, we used area to fill in and compute the area. And you totally can do that now, but we can also just save a little bit of time and use Desmos. Luckily, Desmos has the uniform dist just like it has the normal dist. And we can put in uniform dist from 1 to 5 and find the cumulative probability. And we want to know the probability that x is less than 2.85. And let's bring the picture up here too. That means it's from 1 to 2.85. This area right here, this shaded purple, it actually computes that area for you. We could do it ourselves if we wanted to, but this saves a little bit of time. And that area is 0.4625. So the probability that an individual student's stress score is less than 2.85 is equal to 0.4625. Now, we didn't do anything with the central limit theorem here. We used straight up what we know about uniform distributions, calculated the area that corresponds to this probability, and came up with our answer. Now, let's find the probability that of those 75 students in our sample, the mean stress score is less than 2.85. Well, to do that, we need to do a little bit of work first, right? The individual's distribution was uniform 1, 5. So we first need to calculate this distribution's mean and standard deviation, and then use that to calculate the mean sampling distribution mean and standard deviation. Excuse me. Hopefully you remember that the mean for the uniform distribution is just the average of the two endpoints. So we take 1 plus 5 and divide it by 2 and we get 3. So that's the mean for x. And the standard deviation for the uniform distribution, you remember that as well, is the square root of b minus a squared over 12. 5 minus 1 squared over 12 square rooted, we get 1.15. So there's the mean and standard deviation for our uniform distribution. Still can't answer this question yet, but we do have a little bit more information. Now, we need to find the mean and the standard deviation for the mean distribution of the sample of 75 students. So since the original distribution's mean was 3, remember the mean of the sampling's distribution is also 3. Remember, the means stay the same when you average them. The standard deviations don't. The original standard deviation for the distribution was 1.15. So the standard deviation of the sampling distribution is 1.15 over the square root of n. Remember that formula? In this case, n is 75. So we take 1.15 and divide it by the square root of 75, and we get 0.1328. So now we found the mean and the standard deviation of the sampling distribution x bar, the means, and we know it's distributed normal, 3, 0.1328. We are almost ready to answer the question. Finally, we can now use Desmos to compute the probability that the mean stress score for 75 students is less than 2.85. So we use our parameters that we calculated for the sampling distribution with the mean of 3 and the standard deviation of 0.1328. We want to know that the probability that the score is less than 2.85, that's this area right here, and we get a probability of 0.1293. All right, so what did we do here? When we compared, let's compare what we did in the first one. We just computed for an individual student. What is the probability that their stress score is less than 2.85? We got about 46.25%. But we looked at the average for 75 students. We found the probability that average is less than 2.85 is about 12.93%. And remember why that is. And that's because remember when we average these, the means stay the same, but the standard deviations get smaller and smaller and smaller with your larger and larger samples. So that I'm making hand motions here that you can't see, but that standard deviation is wider over here, right about the same mean. But here it's going to be longer and narrower when we do the means because it pushes them together because we're averaging those values. All right, and let's do one more problem on this. What's the probability that the total of the stress scores is less than 200? Again, this is a sum, so this is central limit theorem. We need to figure out the sum's mean and standard deviation. Remember, for the sum, you multiply n by the original standard deviation, and you multiply n by the original mean, and you multiply the square root of n by the original standard deviation. So our new mean for the sum is 225, and the standard deviation for the sum is 9.96. Sorry, Flocko's over here barking at the door. He's just going to have to wait. So the sums are distributed normal, 225, 9.96. And to find the probability that the total of those 75 stress scores is less than 200, we use a normal distribution calculator in Desmos with this normal distribution, the normal distribution of the sums. And we go from negative infinity up to 200 because we want to know the probability is less than 200. And we get a really small number, 0.006. All right, so that was an example of first just using the distribution to answer a question, then using the central limit theorem to figure out some information, some probabilities about the mean, and using the central limit theorem to find some probabilities about the sum. Let's do one more example. So a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their basic contract, the excess time used follows an exponential distribution with a mean of 22 minutes. Let's consider a random sample of these Eddie customers who exceed the time limit allowed in their basic cell phone contract. All right, so our first random variable X is going to be the amount of excess time used by one individual cell phone customer who exceeded his contracted time. It tells us in the description that this uses the exponential distribution. Now, we haven't actually talked about the exponential distribution yet in this class, but it is a continuous distribution like the normal distribution or the uniform distribution. But in this one, the mean is equal to the standard deviation. And it's a little bit like a continuous version of the geometric. You don't really need to know too much about this distribution because I'm only going to answer questions and ask questions that involve the central limit theorem. However, just a little bit of information. We write X is distributed exponential m, with m being the one parameter, and the mean and the standard deviation are both equal to each other, and they're equal to 1 over that value m. All right, so we are told the average value for X is 22, so we know that that was part of the information that was given. 22 minutes is the average, so we know the mean, the standard deviation are both equal to 22, and we can fill in that this is distributed 1 over 22. So let's find the probability that the mean excess time used by the 80 customers in the sample is longer than 20 minutes. Well, we know by the central limit theorem that if we find the mean's going to stay the same, and the new standard deviation is the old standard deviation divided by the square root of n. In this case, our 80 customers, n is equal to 80. So 22 divided by the square root of 80, we can actually just put it straight in the normal Desmos calculator like that. Find the probability that that is greater than 20, and we get about 0.79. So you don't need to really know that much about the original distribution to be able to use the central limit theorem. In fact, you don't even need to know what the original distribution is if you're only interested in using the central limit theorem to find out things about the mean or about the sum. All right, let's do one more example on the central limit theorem. In the United States, someone is sexually assaulted every 2 minutes on average, according to a number of studies. Suppose the standard deviation is 0.5 minutes and the sample size is 100. Let's find the median, the first quartile, and the third quartile for the sample mean times of sexual assaults in the United States. Now, we don't even know what distribution this is. We just know that it has a mean of 2 minutes, a mean of 2 minutes, and oops, that didn't work. A mean of 2 minutes and a standard deviation of 0.5 minutes. And we are looking at a sample size of 100. All right. We do know by the central limit theorem that if we look at the mean values, that's going to be normally distributed by the central limit theorem. And in fact, we know that mu is going to be equal to the mu sub x of our original distribution was equal to 2. And we know sigma is going to be equal to the original sigma sub x divided by square root of n, which is 100. So that's going to be equal to 0.5 divided by 10, which is 0.05. So this is what we can use the central limit theorem to help us. We can find the new mean and the new standard deviation for the mean distribution of means. So we know that x bar is distributed normal with a mean of 2 and a standard deviation of 0.05. So how do we find the median, the first quartile, and the third quartile? Well, in normal distributions, remember they're symmetric, not skewed. So the mean is always equal to the median, which in this case is going to be equal to 2. I don't know why I'm underlining that. It just looks messy. And how do we find the first quartile? Well, let's remember that's the 25th percentile, right? We know how to find a percentile in a normal distribution. We use inverse CDF. We put in our normal distribution, and we put in the percentile we're interested in, the 25th percentile. And that tells us the 25th percentile is about 2 minutes, 1.97 minutes. The 75th percentile, same deal. We put in the 75th percentile. That's the third quartile. So that tells us 2.03 minutes. So we can find quartiles by using the inverse CDF function in Desmos. And I didn't do a screenshot of Desmos, but this is what I use to do this inverse CDF for. So that's it for using the central limit theorem.